Okay, welcome to class meeting 18 of EECE574, the graduate level probability and random processes. As usual, homework will be assigned and handout for chapter 7 is updated, so please download it again. Let's overview what we've done for this chapter 7, entitled Sequences of Random Variables. Especially in the last class meeting, we studied the equality of two functions and approximate equality of two functions by using a sequence of functions. First, we defined equal everywhere. What does that mean? For every S in the common domain, the function values are the same, then we call the functions are equal everywhere. Or we can use not just this possibly uncountably infinite number of scalar equals scalar equality. We may just use a simple set equality. So this means two functions are equal. So the subset of the common domain such that the two function values are the same equals the common domain, then we call the two functions are equal everywhere. Then what is the definition of two functions are equal almost everywhere? In order to do that, we consider the complement set, and the complement set is simply obtained by changing the equality to inequality in this set definition. And not only we compare this one with an empty set because it is not necessarily empty set, we just take the measure of it. And if this is 0, then we call the two functions with the common domain are equal almost everywhere. So here, what is important is that we compute the size of the set where the two functions are different. Of course, as you see that, if this is true, which means that if two functions are equal everywhere, means that this set is an empty set and the size of the empty set is always 0. So what does that mean? Equal everywhere implies equal almost everywhere. The converse is not true. So this is the first one. This is the second one. Then what is the third one? Equal in the p-th mean. What does that mean? So what you do is that we want to find the integration of the difference raised to the power of p, and then we integrate. And this can be 0 or not, but if this is 0, we may call the two functions are equal in the p-th mean. And interestingly, you can easily show that in the function equality, the second and third definitions are the same for p greater than or equal to 1. And the first one is equal in measure. What does that mean? You again have the measure. You measure the size of a set, and this set is very similar to what we're handling, but it is slightly different. We are not just considering equal or not. We give some margin on the difference. Now consider where epsilon is very, very small positive number, which means that this is the error that is greater than very small number. And if this number is 0 for all epsilon positive, then we may call two functions are equal in measure. However, again, in the two functions equality, the first definition is also the same as the third one, which is the same as second one. So in the function equality, we are just interested in two things: equal everywhere or equal almost everywhere. This situation changes a lot when we want to claim that two functions are approximately equal, so that we construct a sequence of functions, and when we talk about the convergence of a sequence of functions to another function. So here, in order to handle approximate equality of two functions, usually we construct a sequence. After that, sometimes we just find upper and lower bounds and saying that this upper and lower bounds converges to the same number and they are tight asymptotically, blah, blah, blah. Or we may just say that the limit of this sequence is the desired function. In that case, we have one more definition that is not directly related to this form. As you see that here are sequence counterpart of these four equalities. Here are four approximate equalities. The first is the uniform equality, a uniform convergence. And the uniform convergence is like this. For every epsilon positive, there exists n of epsilon, an integer, such that n is greater than or equal to capital N of epsilon implies, let me consider the case where we compare the sequence of functions x of n and a function x of s. Okay, so for n greater than or equal to capital N of epsilon, the difference is less than epsilon. Here is the important part: for all s in the domain. This is very important. So we want to bound we want to bound x of n using plus minus epsilon. And if this is possible for every s in the domain, then we say that the sequence converges uniformly. And this is much stronger than convergence everywhere. And we can construct an example, but it will be deferred to the discussion of other to the discussion of the convergence of a sequence of random variables, which is covered today. So this is the uniform convergence, and everywhere convergence is like this. Of course, we can use for every epsilon, blah, 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 but the first simplest one is that the xn of s converges s of s for every s in domain. And then we say that the function of the sequence the sequence of functions converges to the function x everywhere. And of course, by using the set, we can rewrite like this. S in domain such that xn over s converges to x of s. By the way, it seems we don't need this, right? Because we specified already. Yeah. Okay. This is same as the here we have the limit. So in other words, we can rewrite it like this. For every epsilon positive, there exists n of epsilon integer such that n greater than n of epsilon implies xn of s minus xs less than epsilon. But be careful, in order to show this convergence, actually, we can choose epsilon differently for each s. So this distinguishes the convergence everywhere with the convergence uniformly. Okay. So if you want, you may put it here, something like epsilon sub s if you want. So for each s, you may choose different epsilon, okay? However, in the uniform convergence, you have to choose a single epsilon. That's the difference, right? So you can easily see that if a sequence of functions converges uniformly, then it automatically converges everywhere. Second, convergence almost everywhere means that we take the size measure of the set on which the function does not converge in pointwise. By the way, everywhere convergence is also called pointwise convergence. Because for every point or every value in the domain, we have convergence of a sequence of real numbers in this case. See that if we fix x, see that if we fix s, right? This is nothing but the convergence of a sequence of real numbers. So we use that convergence of a sequence of real numbers for each point in the domain. That's why this everywhere convergence is called the pointwise convergence. Similarly, we define almost everywhere convergence by taking the set. So here, we simply say that this does not converge, and we take the measure of the set, and this is it, okay? So you take the points in the domain on which the sequence of now real numbers does not converge to the real number, evaluated by the function x at s specific s. And then if this set is 0, still you are happy and saying that the sequence of functions converges almost everywhere. Got it? And what was the most seminal example? The scale wave. As we've seen, the scale wave is a discontinuous function. And if you construct a sequence of functions by using truncated Fourier series, then what do you know? At every discontinuity point, the limit is the midpoint between the right and left limits. So the every discontinuity point is not included. So it's included in this set. However, the set has finite, countably infinite number of points. And then the Lebesgue measure of that set is 0. So we have almost everywhere convergence. The problem is that even though truncated Fourier series satisfies this one, of course, it's not everywhere convergence. It's not uniform convergence. And especially about the uniform convergence, we can see that the Gibbs phenomenon gives us the strange behavior. For example, at the discontinuity point, the peak error does not reduce, even though the error energy, the error signal has diminishing energy as n tends to infinity. Anyway, here goes the third one, convergence in the Pitts-mean. So we use something similar to this. So we take the nth term of the sequence and calculate the absolute error and raise to the power of p, and then we integrate. And what do we want? What do we want? We want this. This value is, by the way, a scalar, real value, but it's parameterized by n. What do we have? We have a sequence of real numbers. We want this sequence converged to 0 as n tends to infinity. Right? This is a sequence of real number, right? After we integrate. So from a sequence of functions, we take the Pitts-mean. And the Pitts-mean is a sequence of real numbers. And this sequence of real numbers converges, then we call the sequence of functions converges to the limit in the Pitts-mean. Got it? And the fourth one is also motivated by that one. And what we do is that we calculate a subset of the common domain where the difference between the nth sequence element and the target limit is, let me see, yeah, greater than epsilon. And then since we talk about the convergence in measure, we take the Lebesgue measure of this set if a domain is the real number, and see that what is this one now? This is a real number, right? But it's parameterized by n and epsilon, right? So it's a sequence of real numbers parameterized by epsilon. So for each epsilon of your choice, you now construct a sequence of real numbers. And what do you want? For every epsilon positive, you want this sequence goes to 0 as n tends to infinity. Okay? So this is your definition. By the way, I need something like this, right? Okay. So do you see the similarity here? For every epsilon positive equals 0. Here, for every epsilon positive, the sequence converges to 0. Got it? So we have defined the convergence in measure. And unlike in the equality case, these 1, 2, 3 definitions are different. And we will see the examples later. And we have the relation like this: uniform convergence, uniform. Let me just use the previous page we had. Yeah, so uniform convergence implies convergence everywhere or pointwise convergence, and it implies convergence almost everywhere. But it does not imply or implied by the convergence in the Pitts-mean with p greater than or equal to 0, but both of the kind of branches implies convergence in measure. Got it? So this was what these are what is studied last time. Now today we are going to generalize or apply, because it's kind of a generalization, because we have one more mode of convergence when we talk about the convergence of a sequence of random variables. So since we have one more new definition, it's a generalization. However, unlike the general sequence convergence of a sequence of functions, we have so-called the probability measure, not just some measure like Lebesgue measure. And one important thing with probability measure is that it's finite. So the probability measure cannot be any number. It's bounded by 0 and 1. And that makes a lot of difference. Anyway, so we have interesting new definition, and that is also, of course, related with the equality of two random variables. Anyway, we learn 4 modes of convergences, not only the convergence in distribution we studied last lectures. We studied the almost sure convergence, convergence in the Pitts mean, convergence in probability, convergence in distribution. And then, as we already have seen in our undergraduate programs, we talk about strong law, weak law of large numbers, and the central limit theorem again. And we are talking about Borel-Cantalli lemmas that are very, very useful in proving the strong law of large numbers and also related almost sure convergence. Okay. And then we will see the section 7.5 entitled random numbers, which half of the topics of which are covered already in our undergraduate part. But here we link the random number generation and law of large numbers, and also talk about so-called Monte Carlo integration and Monte Carlo simulation. And probably not today, but finally, we will go back to the sampling and limit theorem section, which was also appeared in our last section of the last chapter of our undergraduate coverage, but we skipped part. And here we talk about sampling, together measurement, and some point estimators, and law of large numbers, and so-called the method of moment estimator. Anyway, so here we have now the topic of equality of two random variables. First question, what is a random variable? And your answer is, it is a function, okay? Of course, it is a measurable function, and the function itself does not mean much. We need what? We need this random number generator or a random outcome generator described by a probability space consisting of the sample space, event space, and the probability measure P, right? And it generates the outcome. And now, if we have a single measurable function, the output of this function is called, usually in undergraduate course, a random variable. But actually, this is random variable, right? The function itself. And now, given the same input, we may have finite number of measurable functions, or we may have countably infinite number of measurable functions. Given a sequence of random variables means that now we have countably infinite number of measurable functions, possibly parameterized by this index n. Got it? So first question, in order to talk about the equality between two random variables, what kind of approach do we need to use? Yeah, we need to use the approach we already studied, equality of two functions. So let's see. Here goes equal everywhere first. So consider the set of S in the sample space such that X of S equals Y of S, right? So you take this set, and if this set equals the sample space, what do you want to say? The two functions, X1 and X2, are equal everywhere, right? But this function has a little bit different name called random variables. So two random variables, X and Y, are equal everywhere, right? This is equal everywhere, but since it's the probabilities involved, we call equal surely. They are equal surely, right? With sure. Right? And second one is that we take the measure of this set, right? Where two functions have different values, and take the measure probability, compute the probability of this event, right? That's the difference. Before it was a general measure M, now we use probability measure P. And if this is 0, what do we say? They are equal almost everywhere, but we better use equal almost surely. But see that we have what? Probability is 0 for the set on which two random variables are different. So what can we say? This is equivalent to this statement. See that? Here I emphasize that when we talk about random variables, the measure of some event, right, which is probability of some event, is finite. That's why we can just use this one. They are the same, right? The complement event has what? 1 minus probability of that event. So instead of using this one, people prefer using that one. But when we studied two functions equality, I preferred using this one with inequality. Why? Because the measure can be infinite in general. But if the measure is always bounded, a finite number like this, then we can just change the form in that way. And this gives us what? Equal with probability 1. And this is called WP1 sometimes, with probability 1. Got it? So with probability 1 means equal almost everywhere, but we prefer to using the term equal almost sure. So these two are the same. And when we talk about the probability, actually this equal surely does not mean much. As I told you last time, as an electrical engineer, we may have interest in the energy of some error signal, not the error function itself, right? Similarly, when we talk about probability, this does not mean much. This is much important, right? That's why they rarely talk about this one. Same in the convergence of a sequence of random variables. So this is the first one. And what is the second one? When we talk about the equality, what can we say? Of course, we can consider the equal in the Pitts mean, but as I told you in the equality of two functions, they are the same, right? So as you see that these three were all the same for the equality of two functions. Got it? So here we have something new, which is very interesting when you talk about probability. Consider remember one of your exam homework problem. Suppose you have random number generator, which is uniform 0, 1. Now you have two functions. First one is just a deterministic mapping rule, of course, x equals u. So you have the output so-called x. And here you have y, that is 1 minus u, and the output is the random variable y. Now, question, is x the random variable equals to the random variable y? If it is equal, in what sense? Okay. So whenever you are asked such a question related to two jointly distributed random variables, your standard approach is to consider what? 2D histogram, right? Now, suppose u is 1. What happens? 1, 0. U is 0.1, 0.1, 0.9. So you can easily guess that the scatter plot will look like this, right? Definitely, these two functions are different, right? Now, just consider the PDF or CDF of these two random variables. What can you say? Actually, if you convert the lower one with variable x, they have the same PDF. If you choose to have right continuous blah, blah, blah. Well, if you hate that, just use the CDF. Okay, so you have the CDF of x and CDF of y. And now you consider CDF of y as a function of x. Okay, then these two CDFs are the same, right? If the output distributions are the same, but two functions are different, but still you want to say that they are equal in some sense, what would be that? They are equal in distribution. Got it? So this is called equal in distribution. So if CDFs are the same in distribution, here goes the definition. If the CDF of x equals CDF of y for all x real number. Got it? Now question, suppose these two are general mapping rules, general random variables. When do we say they are equal? The 2D histogram is exactly what? On this line x equals y, right? Then they are equal everywhere, equal surely. However, what happens if the probability of event that x equals y is 1, but there could some very unlikely outliers that is not on x equals y. You say that they are equal with probability 1. They are equal almost surely. Got it? So by thinking about the equality of two random variables, we not only have the almost sure equality or equal with probability 1, we found that the equal in distribution is an also interesting definition in some cases, but they too must be differentiated, distinguished. Almost sure equality implies equal in distribution. However, the converse is not true, as you've seen here, right? So this almost sure equality implies the equal in distribution, but the converse is not true. Now, let's consider the sequence of random variables. The first question is this. When we talk about the sequence of random variables, what would be the limit of that sequence? It could be anything, or it should be something. And if you remember our previous review on the sequence of functions, our target is, of course, a function, right? So when you talk about the limit of a sequence of random variables, the limit, if it exists, must be a function. It could be a measurable function. Then we call that it is a random variable. So we are interested in the case where, given a sequence of random variables, its limit is a random variable or not. So we have a sequence of random variables x sub n, and we have a random variable x. And we check whether this sequence converges to the random variable. Got it? Since they are all functions, we can immediately use those definitions we introduced. However, as I already told you, when you talk about the probability of event, even in talking about equality of two random variables, we didn't like that equal everywhere. What is the counterpart in the convergence of a sequence of functions? Convergence everywhere. We don't need that. That's what I'm saying. Okay. So here goes a kind of a summary. Convergence everywhere is not useful when you talk about probability. Much stronger one, convergence uniformly, is not useful either when you talk about probability, because some event has meaning only when it is evaluated by the probability measure, when it is converted to the probability of event, not just the event. Got it? So what is important is what? First, the convergence almost everywhere, which is related to now convergence almost surely, or convergence with the probability one. And second one with convergence in the piecemeal with p greater than or equal to 1. And convergence in measure. Now it is called convergence in probability measure, or simply convergence in probability. Okay. And the fourth one is related to what we've just seen for the equality of two random variables, where we introduced the notion of equal in distribution. Similarly, we have convergence in distribution. Got it? So there are 4 modes or versions or different definitions of a convergence of a sequence of random variables, the convergence of a sequence of random variables to a random variable we are interested in. First, almost sure convergence. Second, convergence in the piecemeal. Third, convergence in probability measure or convergence in probability. And finally, convergence in distribution. You have to differentiate these 4 definitions. And let's see. So this is the first one, convergence almost surely. See that? We just write in this way. Xn tends to x a dot s dot. What does that mean? See that probability of the event equals 1, right? The probability of this event is 1. So converges with probability 1. Got it? And convergence in the piecemeal means this one. Why? Because before we had something like this. Now, this is changed to what? Sample space. You have the error difference. And what is this? Probability measure, right? Not just a arbitrary measure. So what is this? This is expected value of value times probability means that one. Got it? That's why suddenly we have that appeared. And we want what? This is a sequence of real numbers, right? See that? It's parameterized by n after you compute the expectation. This goes to 0. This tends to 0. Got it? So if you want to use this notation of right arrow, actually, this can be written as this one, S in the sample space where xn of s tends to x of s equals 1. So here you use this 2, the right side. And also, if you want to say that this goes to 0, right? See that? Limit. And what about the third definition in probability? See that here, for every epsilon positive, you construct a sequence of probabilities. And that sequence converges to 0. So here again, for every epsilon positive, your sequence of probabilities goes to 0. Okay. Again, you have the limit, right? So sometimes these are easier to memorize because they have what? The limit operation explicitly using the right arrow, not just the limit. Okay. If you prefer using limit, you just use in this way. But sometimes people prefer that one. And the last one is interesting. As I told you, we have a sequence of CDFs. And this converges to the sequence of the target, the limit CDF, right? Here, not for every x. For every x, every continuity point. Why we need this? Because in some cases, we have some problem. Okay, we will see the example. Okay. So there is another alternative definition that is very useful, as we've seen. What is that? We consider the sequence of characteristic functions converges to the characteristic function for all omega. Okay. And we need pointwise convergence. Okay. Then we are good. Okay. So let me give you the notations. Xn tends to x. Xn converges to x with probability 1. Xn converges to x in LP, or Xn tends to x LP in LP, or in the piece mean. Here, on top of right arrow, people put P, and Xn converges to x in probability measure, or probability. And convergence in distribution is denoted this way. Xn converges to x in D distribution. Got it? And we have a similar relation among these 4 definitions. And it is summarized in this figure. I prefer using this kind of flowing down to in distribution. Some people love counterclock rotated version of this figure. So they start from the left-hand side and flow to the right. But anyway, Myself call this as kind of Y diagram, and it looks like alphabet Y. So here is the almost sure convergence, and here is improbability convergence, and here in distribution convergence. On the right branch, we have convergence in the piece mean for P greater than or equal to 1. So actually on the right branch, we have uncountably infinite definitions which can be grouped and called just convergence in the piece mean. So we have 4 modes of convergence. By the way, I also told you that when we approximate a function using a sequence of functions, or we approximate a random variable using a sequence of random variables, just showing that it converges is not enough in some times. We need to find the upper and lower bounds. In that case, as n tends to infinity, you want to show how fast the gap diminishes. So not only finding the limit, but also finding the rate of convergence is often very, very important in mathematical analysis. And that is translated to the performance analysis in electrical engineering. So if you want to do research in this area, or you need to do, then you need some knowledge, background knowledge in the real analysis and measure theory. Okay, so here are some proofs related to this Y diagram, but I will not cover all of them because it takes too much time. Okay, and also it requires, as you see that here, we use the Borel-Cantelli lemma. We haven't yet covered, and I'm not going to talk about everything. I will just show you some examples where these definitions does not imply the other definitions, something like that. So I will give you counter examples. Got it? So let me see. Yeah. First, let's see the case where almost sure convergence does not imply convergence in the second mean. Okay. So here, in order to make everything simple, we consider some cases like this. So here we have the random number generator that generates, in this case, I noted omega, but this is uniform 0, 1. Continuous uniform random variable on this interval. So actually, we have a uniform random number generator, and the output is mapped to another random variable by using this function. See that this function has function value 1 plus n for the interval 0 to 1 over n. And for the rest of the interval, its value is 1. Now, what is x sub 0? What is x sub 0? X sub 0 is the function all 1, right? What is x sub 1? You have, so let me draw. X sub 0 is this one, 1. Now, x sub 1 is what? So for the interval 0, 1/2, you have value 2. And for the other, you have 1, right? Now, what about n million? This value goes up and up and up. However, its interval diminishes to 0 to 1 over million, right? So very small. Now, first question, does this sequence of random variables converge to what? What is the limit? What is the limit, you guess? Just as an engineer, take a sufficiently large number, million, for example. Then you have what? For this interval, value is 1. And for very small interval, it's very large, but that probability is very small. So it seems that we want to test whether the function 1 is the limit. By the way, if we have some function that is 1, what kind of output do we have? X is what? X is a constant random variable. So it always generates 1 with always generates 1, right? So this equals 1 in some sense, right? But anyway, this is very special case. However, it really gives us counterexamples. That's why we love this one. And in most of the textbooks actually love it. I myself didn't devise this example. I was also taught in one of the textbooks. Got it? So now let's check. First question. Does this sequence of random variables converges to random variable x equals 1 everywhere? First, everywhere? Even though that is not important, as I told you. Let's warm up. So do we have everywhere convergence of this sequence of random variables to x equals 1 for all omega? Now see that for every omega between 0 and 1, excluding the endpoints, of course, you can include 1. What is the limit at each point? Of course, at each point, our limit is 1. However, at the value omega equals 0, the limit does not exist. It diverges, right? What about other? It doesn't matter, right? Because our omega is between 0 and 1. As I told you, it's a uniform between 0 and 1, including the endpoints. So what can you say? This sequence of random variables does not converge to the random variable x equals 1 for all omega because of that single point omega equals 0. In that sense, this sequence does not converge surely. What about almost sure convergence? Yes, because the set on which the sequence does not converge to that function contains only one element, and that element's probability of event is 0. So almost sure convergence is guaranteed. Now, almost sure convergence implies the convergence in the second mean. So in order to check, we compute what? We compute the mean squared error. So we construct the sequence of mean squared errors, and we want to see whether it goes to 0 or not, right? If it converges to 0, we have established the convergence in the second mean, or limit in the mean is 0, right? Or limit in the mean of xn is x. Now let's see. In order to compute the probability, we need to multiply value times probability. What is the value? N plus 1. What is probability? 1 over n. So we have n plus 1 times 1 over n plus, it's squared, so actually this one is what? The value n plus 1 squared times the probability plus the value squared. See that? Sorry, we have to subtract. I'm sorry. So first we subtract n plus 1, 1 from n plus 1. So n squared times 1 over n. This is value of this one, right? This is the probability. Plus, what is the value? Now 0 times 1 minus 1 over n, right? What is this one? This is n, and n does not go to 0 as n tends to infinity. So we've just established that the almost sure convergence does not necessarily imply convergence in the pith mean. We can similarly show that the other values of P, we can say almost the same thing. Got it? Now, let's see from this example, whether the sequence of random variables converges in probability. Question: does this sequence converges to x equals 1 in probability? And we know the result. I already told you that from the Y diagram. Well, let's check it. So we construct what? We construct for every epsilon positive, we construct the sequence of what? Probabilities. So probability of event that xn greater than epsilon. The problem is that this sequence value depends on epsilon. So let's take a specific epsilon, very small, 10 to the million, 1 over 10 to the million. Now, what is this value? Given n greater than 1, let me see, or greater. Okay. Difference is greater than epsilon. What is that? Difference is greater than here, right? So we have this probability is always 1 over n, right? Because this is already 2. The difference is 1, right? And this sequence, what? Converges to 0. What does that mean? We have our convergence in the probability measure. You choose any epsilon. Eventually, we have something like this, right? So in the Y diagram, we've seen that we have an example of almost sure convergence that does not surely converge. That does not converge in the second mean, but it converges in the probability measure. What about the CDF, PDF? Anybody? So let's see the CDF. What is the CDF of xn? So given that, what? You have some value 1 and very large value n plus 1, right? Sorry, the value 1 and n plus 1. So here you have 1 and very, very large value n plus 1, right? And your CDF looks like what? It's 0, 0, 0, 0. And here you have what? Jump discontinuity, right? This value is 1. And what is this one? What is this value? 1 minus 1 over n, right? See, the size of this interval is 1 minus 1 over n, and size of this interval is 1 over n. So here, this difference is 1 over n, and this difference is 1 minus 1 over n. So you have this continuous, but stepwise continuous function. Now, what happens if we increase n? This value is 1, right? And this height goes up and up and up and up and up, right? So for sufficiently large n, we have a function that just steps up and almost 1. And very far away, we have a small jump. Now consider the limit. For each value of x, what happens? Any finite value less than 0, the limit is 0. Greater than 1 and less than n plus 1, it's definitely 1. But what about some specific large value? If n is greater than that value, right, then what happens? It goes up and up and up and up. So you can easily see that for every finite x, you have what? For every x real, right? Consider very large number. And if this is small, then you have some problem here, right? However, if n goes large, then this goes up and up and up, and this moves right away, right? So you have the convergence in distribution. Adi? What else do we have? It seems I don't have other example here. But anyway, it seems that this is good enough for some counter examples. I remember I put more examples. Where are they? It seems I've taken them out because they are too lengthy. But anyway, so we've just introduced 4 modes of convergence of a sequence of random variables to another random variable, right? Now, what is the use of it as an electrical engineer? There are 4 modes of convergence, so which one do you want to prove? Fortunately, in many cases, it is enough to show the simplest one by definition, the convergence in distribution. However, definitely sometimes you want to, for example, plot something and show that you have some almost sure convergence. What does that mean? As n tends to infinity, the kind of gap between 2 parallel lines to x equals y becomes smaller and smaller, smaller. So it's like this is xn axis, this is x axis. And when you have some n, 5, then you have some dots here. If you increase n, then you have some narrower gap, right? And that gap becomes smaller and smaller and smaller, smaller. Sometimes you want to show that. And that is definitely what? Convergence in almost sure sense. So we need different techniques to show the convergence in almost sure sense, in the Pitts mean, in the probability measure, in distribution. And let's see some example. Suppose you have let me see. Yeah. Just a second. Let's see. Yeah. What can I do? Just a second. Okay. Consider this problem. Suppose you have observation y that is square root p times bit. Here, bit is either 1 or -1, and plus square root p sub I, and here you have n terms. X sub I, let me think. Yeah. And you have noise. And here n is Gaussian with variance sigma square. And here xi is IID with probability of xi equals 1 equals probability of xi equals -1 equals 1/2. And also, let's assume that b is either 1 or -1 with equal probability. So it's a communication problem. You receive the channel output y, and it contains the desired signal component in additive white Gaussian noise, and you also have an interference. Now, you want to analyze the performance of your simplest receiver that is given like this. So you have B hat equals sine of Y. So this is your receiver. And you want to find the probability of bit error of that receiver. So you want to compute, actually, you want to compute this probability. And what can you say about this probability? Actually, this is nothing but the probability that let me see. Yeah. Square root P sub I, 1 over square root N, summation of N interferences plus noise is greater than negative square root PB, P, given, just a second. Yeah, we don't need condition. We are asked to compute this probability. It's actually same as the conditional probability of bit error given B equals 1. Okay? And due to the symmetry, we have that. Now, I'm asking this probability, and you know that from the central limit theorem, this one is very close to a Gaussian random variable if n is very large, right? Right? So instead of using the exact probability distribution to find this probability, you want to just claim that this is approximately equal to a Gaussian random variable. So you want to say that, hey, this is approximately equal to a Gaussian random variable x that has what? Mean 0 and variance pi. If you compute the variance of this sum of random variables, because we have square root n, the variance has 1 over n, and we have n terms times of variance of this one, n, which is 1. So our variance is just p sub I, right? Now, what if we have established the approximate equality between this one and that one? Since this is also Gaussian, it's very easy to compute this probability. And what is this probability now? After approximation, probability of event that x plus n greater than negative square root p is equal to q of, if you use the CCDF of the standard Gaussian, we have what? Something like this. We just add up two variances here, and we have the threshold square root p. This is what we want to do as an engineer. But we cannot just simply write, hey, this is a good approximation. We want to show this approximation is really good mathematically. Then what do we do? Now, what is our objective? We want to show that this probability is very close to that probability when n is sufficiently large. When one kind of convergence shows that, actually, convergence in distribution is enough, right? We just want to show that, let's say that, let's say this is the random variable. And what is that? It's CDF, right? Simply, this is a CDF of this random variable evaluated at negative square root p. And this is what? This is the complementary CDF of x plus n evaluated at negative square root p. So exactly, this is the case where convergence in distribution is enough to prove our approximation is very good, right? So when I joined my professor, my thesis advisors group, one of the recent paper was using the convergence in distribution to claim that some systems' performance can be well approximated by some Gaussian, using by Gaussian approximation. And our seniors used convergence in distribution to prove that. And what would be the most simplest tool? The characteristic function. So they use the characteristic function, converges to the Gaussian characteristic function. And that's all. Got it? But if you want, you can show the convergence in almost sure sense because it implies convergence in distribution. Even though in this purpose, it's enough to use convergence in distribution, given the receiver's performance, sometimes some other researcher may need to use the convergence almost sure sense. For that, you'd better prove not just your target proof, you may prove much stronger version if you can, okay? So some of the papers was showing, some of the seniors were showing convergence almost sure sense, got it? So depending on your needs, you must be able to choose one of the modes of convergence. Now see that, can we just use convergence in the second mean? Actually, we can do that. So we subtract this one from that one, and we do something. The problem is, in order to compute the other four modes, we have to have jointly distributed random variables, right? See that? We have same function. We don't need, in the last definition, we don't need actually same source generating two random variables. We don't need this x jointly distributed this axis actually. However, for other convergence modes, we need that one. So it's not that simple. Got it? Anyway, so we've seen one of the examples in engineering, in communications. By the way, these four modes have some very good examples. First one is the strong law of large numbers. Law of large numbers, as you remember, is related to what? The arithmetic mean converges to the statistical mean in some sense. And if that sense of convergence is almost sure sense, the theorem is called a strong law of large numbers. So here, strong means almost sure convergence. Law of large numbers can be proved in a more weaker version that use convergence in measure. In that case, we call it weak law of large numbers. By the way, as you remember, central limit theorem use what? The convergence of the standardized characteristic function converges to the characteristic function of standard Gaussian. So central limit theorem is related to the convergence in distribution. What else do we have? By the way, for the weak law of large numbers, usually what it proves is this one. See that? One of the examples is weak law of large numbers, but you see this branch, right? So what we do is that we choose p equals 2 and proves that the arithmetic mean converges to the statistical mean in the second, the limit in the mean of the arithmetic mean is the statistical mean, because that implies that one. So here they talk about Chebyshev inequality and something like that, because Chebyshev inequality, by using that, you can use the actually link the second mean with the probability. Got it? Anyway, this is the proof. And
Dr. Joe, it is time to wrap up.
Central limit theorem example. And this is too tricky. Let me skip. This is covered. That's covered. Yeah. And this is the topic related to the Borel-Cantelli lemma. And in order to understand what's going on with that lemma, actually, we need a lot of preparation. I'm not sure it's worth to cover in this course because it takes a lot of time. So let me think about it during the weekend. And if I believe that there's too much, I will skip this part. Okay. And if I believe it's worth to do, then we may spend 1 more week or half of the week on this topic. And then we eventually move to the next one, random processes. Got it? So let me think about it during the week.